Hello and welcome to Leonard's Education Centre. I am your host, Lena, and today we're doing computer science topic 1.1.1. It is one of four from the 1.1 section. So you have 1.1.1 through 4. 1.1.4 is for A-level only, so keep that in mind if you're an AS student. Please note this is OCR spec, and that I myself am a student. Now, I wouldn't make something if I didn't think I was confident in a topic, but please keep that in mind. So 1.1.1 is a pretty big topic as far as like our little subtopics within computer science go. There is a lot of stuff you do just need to remember. There's not like a lot of theory behind it. It is quite a big memory topic. So we'll start right back at the basics. So first off, what is the CPU? Everyone talks about it, but simply it is the brain of the computer. It processes the data, all of the instructions, all decision making, all calculations, anything like that on a computer goes through the CPU. How does it do that? Well, it starts with the fetch, decode, execute cycle, which simply is a looping cycle, so it will go round like this in a loop forever and ever, as long as your system's powered, that is. It starts at fetch, then to decode, then to execute, back to fetch. Simply put, fetch is where instructions and data are gathered from the RAM and stored into the CPU's temporary memory known as registers. We will come back to registers in a bit. But just know that that's where the data ends up. Then we move on to decode, which is quite simply, what does this instruction that we have just gathered mean? What does it want us to do? Does it have multiple parts? So it breaks down the instructions into individual parts that it can work on and execute. As far as executing goes, that is quite simply, let's do it. What needs to be done, let's do it. Calculations, decisions, evaluation, all of that stuff happens here. And then once you've executed one instruction, you go straight back to fetch, grab the next instruction, decode it, what does it mean, what are we doing? Once we know what we're doing, we go back to execute and go on like that forever. Then what happens in more detail? So let's get into it. So this is the structure of the CPU. Imagine this is all within one chip like this. So you have the control unit up here. The control unit is the brain. It controls all of the other components, so everything you see listed here is controlled by the control unit. It sends signals to control literally everything, so it coordinates movement of data, instructions, it tells the RAM, ALU, registers, input and output what they are doing. Then probably the next most important one is the ALU, which is actually an acronym for Arithmetic Logic Unit, very fancy name, but any calculations or decision making is done by the ALU. Next up we have the registers, as I spoke about a minute ago. This is the CPU's own temporary memory. It is extremely quick and they are a key part of the fetch, decode, execute cycle. We will break this down here in just a minute once we've gone through some other stuff. But keep in mind that they are like small bite-sized storage almost, and without them you wouldn't be able to do the FDE-Cycle and nothing would run. Then, more importantly, their bigger, older brother, we have the RAM or main memory. This is to hold data and instructions that are in the queue to be processed. Nothing has been done with them yet, they are just sat there waiting. And then we have these lines linking everything. These are our data buses. Well, not necessarily data buses, just our buses, sorry. And they move different things between different parts. You can see all of them are connected to every single one, like each sector. So these parts up here are called sectors. Each sector is connected by their buses. So the data bus is strictly moving data and instructions. So This will typically be from main memory to register, or an input and output to the register. Address bus is where the data is stored on the RAM. Its location gets taken from the RAM to the register. This can be done through the use of an input or output device, depending on what's prompting this data move. Then we have the control bus, which links directly with the control unit. It's how its signals get to the RAM and to the input and output devices. As for our register breakdown, before we can even talk about breaking them down, we need to know a couple of key definitions. So we have clock speed, which is a fixed speed at which the fetch, decode, execute cycle happens. It is measured in hertz. If you do a science subject, physics that is, you may know hertz as a wave frequency. It is very much the same, it is just the frequency at which stuff happens. However, for our CPUs, it is typically in gigahertz because they are so fast. Gigahertz are 1 times 10 to the 9 bigger than a hertz. That is 1,000,000,000 hertz. And you can see modern day CPUs reaching between the 5 to 6 gigahertz range. As for what hertz actually means, 500 hertz, not gigahertz, 500 hertz will mean 500 cycles of the fetch, decode, execute per second. Now, although clock speed is a fixed speed, this fixed speed can be changed by something called overclocking, which increases the clock speed. However, this comes at an extreme cost for heat, and if you don't know what you're doing and aren't careful, you can damage your hardware quite seriously. However, you can get massive performance gains out of it. It's a bit of a risk versus reward scenario. Another thing we need to know is cores. So we all imagine a CPU as one single chip. Let's get some permanent ink. A single chip like this that processes all of the data. Well, if we were to zoom in on this chip, imagine inside, instead of it being one fixed chip, you have like 4 different chips there. Let's label them. Don't know why I'm counting down. But each of these chips can run an FDE-Cycle on their own, separately from each other. So this essentially works as quadrupling the speed. And you have different types. So you have dual core, which is 2. You have quad core for 4. There is a name for the others. It's not strictly something you'll be tested on, it's just something to know. But they all have their own unique names, up to I believe 10 for a deca core, but I'm not quite sure on the names of 6 and 8. Now we can get onto our register breakdown. These will all be used during the FDE-Cycle. We'll do a quick example down here in a sec. But first off, we have the program counter. This just simply tracks the number of programs you've been going through. So let's say your program, or your algorithm, has 9 different instructions in it. This will count up 1 through 9 as you go through them. The memory address register, or the MAR, you can simplify all of these down to their underlined characters, by the way. So the memory address register is the address of the instruction that has just been fetched. It's just to help keep track of where we are within the algorithm we're running. Just realized a small mess up here. This is supposed to be memory data register. There we go. It's quite similar to the memory address register, but it holds the value of the data or instruction. So this holds the address. So the address register holds the address. So for example, slot 1 on your memory. Whereas the memory data register would hold the instruction or data in there. So say the data was just 5, it would simply just show 5. Now the current instruction register is also quite similar to the MDR, however it is specifically for the instructions so we know what we're processing. So let's say we were doing this in assembly and it was STA. This would be stored in here and in here. But if it was just a piece of data like 5, the 5 wouldn't come down into the current instruction register. Then we have the accumulator, which holds the value of any data that's being worked on. So if you had 2 separate instructions that call on a piece of data, so let's take our 5, and then say we had an instruction like, I don't know, sub2. The sub2 would be stored in the current instruction register, and then once it's executed, the accumulator would hold 3. We're going to get onto our example of this. So we have our setup here. We're going to separate our table here. Just imagine the iterations. So our program counter starts by going to 1. No, sorry, we're 0 inclusive. I'm making a blunder. We're 0 inclusive, so it starts on 0. The memory address register initially just copies the program counter, so it's 0. The memory data register then looks at this value and then finds the corresponding value up here and loads it into itself. So it will display LDA4, which just stands for load. Next, the instruction register checks whether what has just been loaded is an instruction. It is. So it copies the value of above. So it will also be LDA4. And this is now the instruction we're currently working on. So the accumulator will pull the value of memory address register 4, which is over here. So it's going to pull 5. Then this up here will switch to blue for the next round. Oh, that's a very thick pen. 1 second. Then the program counter will shift to 1. The memory address register will shift to 1. The memory data register will check this value once again. It's now changed to a 1, so it's going to go up to here and gather the data from 1, which in our case is sub 5. Then the instruction register checks if this is an instruction. It is. So it copies the data, which is sub 5. This is now the instruction we're working on. So it looks at cell 5 up here, and it uses the value we have in the accumulator, which is 5, and it's going to take away the value we have in the slot, which we slot to. So we end up with an accumulator of 3. Next pass, we'll go green. Is this going to be big pen? No, it's a small pen. Our program counter shifts to 2. I'm going to work my way outside the box. I know that's a little frustrating. Our memory address register, going to call 2. Our memory data register looks at this value. It's changed, so it's going to pull the new data from cell 2 up here, which is STA6. Our current instruction register looks if this is an instruction. It is. So it executes this instruction. STA in LMC, which is covered in, I want to say, either 1.4 or 2.4, I don't remember which. But the instructions we're using are in LMC, and STA stands for store. So the value that we have in the accumulator down here, which is now 3, is going to be stored in ID 6. So what happens is this value gets taken up to here, and it gets inserted into here. Then despite the fact we know there's no more instructions, we're going to iterate one more time. So your program counter will shift to 3. Your memory address register will shift to 3. Your memory data register notices the change in this value, and it goes to fetch the data from cell 3, so it comes up here into address 3. There is nothing, so it returns 0. Your current instruction register now looks at this and goes, that's not an instruction, so it doesn't copy any data. Because it's not copied any data, there is nothing left to execute, and the program will just stop. It is worth mentioning, when the 3 from down here, in the last pass 3, in the green pass 3, was stored into cell 6, the accumulated then has the value of 0. If it were to be a program that would run, let's say, a totally different related command. So this would have been done in 2 clock cycles or 3, depending on the type of processor, on the structure of it, which is covered in 1.1.2. As for one more thing you need to know out of 1.1.1 is something called pipelining. Now, pipelining is using the output of one instruction as the input of the next. So you can see we've got 2 lists here which are nearly identical. They both have washing and drying a set of clothes, and they have time of day, so you can see it counts up in hours, so each wash takes an hour, each dry takes an hour. Without pipelining, which is this top table here, so hold on, with so without pipelining here, you can see when wash 1 ends, we start to dry the first set of clothes. Then we wait for that to finish, put the second lot on. Once that's finished washing, we put the second lot on to dry, wait for that to finish drying, put the third wash on, etc. And we keep going. And that takes from 10 AM to 5 PM, or 1, 2, 3, 4, 5, 6, 7, 8 hours. Whereas if this was pipelining setup, you can see once wash 1's finished, it starts dry 1, but at the same time, because the washer isn't being used, wash 2 also starts. Then when they both finish at 11, you start drying the second set of clothes, and you start washing the third. Same thing again, when they finish at 12, you start drying the third set, start washing the fourth set. Then, because there's not a fifth set to wash, the fourth dry just starts after their finish, and we end up finishing at 3 PM, which is 1, 2, 3, 4, 5, 6 hours. So in this scenario, it saves 2 whole hours to use pipelining. Now, obviously, in computer programming, this wouldn't take hours. This would be probably the difference between clock cycles. So using pipelining would realistically be 2 clocks quicker. But if you imagine this is one algorithm out of 7,000 that you need to do, saving 2 clocks per algorithm is going to be a substantial save. However, all good things come with drawbacks. And let's say, I don't know, dry 2 for some reason, the clothes aren't done in time and they end up taking an hour and a half. Let's permanent ink this, an hour and a half. You then can't start dry 3, and because of that you can't start anything else in time, and therefore the rest of the order needs to be flushed. This is the key term for it. If your order has to be scrapped in pipelining, it is flushed. And that cancels out any benefit that pipelining would have given for that algorithm. So, say this happened on the first step, it didn't take as long as anticipated, the entire rest of it would have to be scrapped until you're onto the next algorithm. I believe that is every key thing you need to know for 1.1.1. There is some other general knowledge that you should know if you did GCSE. If not, I'd advise you to just have a quick look over 1.1.1. There's some great notes on Physics and Maths Tutor that go over it in really quite simple terms. Thank you for watching, and I hope to see you for 1.1.2.